Hello there, and welcome to the Sleepy Science Channel. Tonight, we'll be drifting far back in time, to an era where the universe was still learning to shine and discovering what it would one day become. Long before our sun was born, before planets even existed, there were the very first galaxies. Vast gatherings of ancient light taking shape in a young and turbulent cosmos. Some were small and restless. Others grew faster than we ever thought possible. All of them were part of a turning point when chaos and darkness began to give way to structure and order. As we wander through this early chapter of cosmic history, we'll move across unimaginable distances, following light that has traveled for billions of years just to reach you now. These distant galaxies are not just far away. They are windows into the beginning of everything. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is relax. Let your body soften and allow your eyes to grow heavy. And let your thoughts drift outwards as we explore the early universe together. Let's begin. Looking at ancient galaxies means watching light that began billions of years ago. Every time a telescope finds one of these remote systems, it is doing something almost magical. It is catching light that set off across space billions of years before humans existed. That light has crossed an expanding universe, passed through emptiness beyond imagination, and survived long enough to arrive here as a message from deep time. So when astronomers point their instruments toward these galaxies, they are not seeing them as they are now. They are seeing them as they were when that light first left them. In everyday life, sight feels immediate. You look at something, and it is simply there. In astronomy, sight becomes history. Distance turns into time. The farther away a galaxy is, the farther back into the story of the universe we are looking. That is what makes these objects so gripping. They are not only far beyond reach. They allow us to witness a past that would otherwise be gone forever, still shining across the ages. The earliest galaxies helped turn the young universe from foggy to clear. After the Big Bang, the universe eventually cooled enough for atoms to form, but it was not yet the transparent cosmos we know. Space was filled with hydrogen gas that trapped the most energetic light, leaving the early universe murky in a very real sense. Then the first generations of stars and young galaxies began to blaze. Their radiation pushed into that fog and started breaking the hydrogen apart again, clearing vast regions of space. This transformation was not instant. It happened piece by piece, as more galaxies lit up and more pockets of darkness gave way. In a way, the first galaxies were not only building themselves, they were changing the entire medium around them. They helped make the universe visible across great distances. Without that long clearing process, light would have remained trapped, and the grand cosmic view we enjoy today would never have emerged. These early systems helped open the universe's eyes, and ours as well. Some ancient galaxies grew far faster than astronomers thought possible. For a long time, astronomers expected the earliest galaxies to be tiny, dim, and slow to assemble. Then better observations began to reveal objects that seemed to have grown with startling speed. Some looked brighter, larger, and more evolved than many models had predicted for such an early era. That does not mean the universe broke its own rules. It means the rules of growth in the young cosmos may have been more intense than we first imagined. Gas was flowing in, stars were igniting, and gravity was building structure at a furious pace. In those first chapters, the universe may have been a place of frantic construction rather than cautious beginnings. That idea is thrilling because it changes the mood of cosmic history. The opening scene is not a slow fade in. It is a rush of formation, a burst of assembly, a time when some galaxies seem to have risen almost overnight on the scale of the universe, surprising even the people who study them. A few early galaxies were surprisingly bright, crowded, and chemically mature. You might expect the earliest galaxies to look raw and primitive, filled with fresh gas and little else. Yet some of them seem to have already moved beyond that first stage. Their light suggests dense regions packed with stars, along with evidence that earlier generations had already lived and died there. That matters because heavy elements do not appear out of nowhere. They are forged inside stars and then scattered by violent stellar deaths. So when astronomers find signs of chemical richness in a very early galaxy, it hints at a hidden past of rapid star birth and destruction. These systems were not only shining, they had already been busy. That gives them an almost impossible feeling, as though we have arrived at the dawn of a city and discovered its streets already full, its furnaces already burning, and its history already underway. The young universe may have matured in patches, producing places that seemed strangely advanced, while everything around them was still just beginning. Some ancient galaxies were already shining when the universe was a baby. When the universe was only a few 100 million years old, it had barely begun by cosmic standards, and yet whole galaxies were already alive with starlight. That is one of the most astonishing things astronomy has revealed. These were not late arrivals. They appeared while the cosmos was still young, hot, and changing fast. Imagine a universe with no mature planets, no settled spiral giants, and no long history behind it. And still there were great islands of stars gathering in the dark. Their light began its journey long before Earth existed, and only now is it reaching our telescopes. That means when we study them, we are not guessing what the early universe looked like. We are seeing it. These distant systems tell us that structure rose quickly from simplicity, and that the cosmos wasted no time building beauty out of darkness, gas, gravity, and the first bursts of fire. The James Webb Space Telescope can spot galaxies that formed only a few 100 million years in. This telescope was built for moments like this. Its mirror gathers faint infrared light that was stretched by the expansion of the universe, allowing it to detect objects far beyond the reach of older instruments. Many of the earliest galaxies no longer shine mainly in visible light by the time their signals reach us. Their light was pulled redward across billions of years, slipping into wavelengths that Webb was designed to see. That makes it less like an ordinary telescope and more like a machine built to recover lost beginnings. With it, astronomers can search the era when the first substantial galaxies were appearing, only a few 100 million years after the Big Bang. That is breathtakingly early. It means we can study the universe while it was still in its youth, when the first large structures were taking shape. Webb does not merely extend our sight. It lets us open a door into cosmic dawn. Ancient galaxies show us how the first great cities of stars began. A galaxy is not just a scattered collection of suns. It is a gravitational community, a place where stars, gas, dust, and dark matter are bound together into something larger and longer-lived. In that sense, the earliest galaxies were the first great cities of stars. They were where matter gathered, where stellar generations began to shape their surroundings, and where the long architecture of the universe started to rise. Before them, the cosmos was simpler. After them, it became richer, layered, and more structured. That is why these systems matter so much. They mark the point where the universe began organizing itself into durable homes for future complexity. Not every early galaxy survived unchanged. Many merged, grew, or were torn apart. But they set the pattern. They were the first places where stars did not merely appear in isolation. Studying them lets us witness the birth of cosmic neighborhoods, the first great gatherings from which later galaxies, planets, and eventually life would descend. Some early galaxies may hide black holes that grew almost unbelievably fast. One of the great shocks of modern astronomy is how early some enormous black holes seem to have appeared. These are not ancient black holes in the sense of being old now. They were already huge when the universe itself was still young. That creates a real puzzle. To become so massive so quickly, they must have grown through intense feeding, unusual beginnings, or processes we do not yet fully understand. Some early galaxies may have sheltered these monsters in their centers, hidden within bright star-forming regions or behind thick clouds of dust. If so, those galaxies were not only places of creation, they were also homes to objects that bent the story of growth around themselves. A black hole can shape how gas moves, how stars form, and how energy escapes into space. So the discovery of fast-growing black holes in young galaxies suggests that cosmic dawn may have been stranger and more dramatic than expected, with creation and extreme gravity rising side by side. The oldest galaxies look small, but they changed the whole universe. By modern standards, many of the earliest galaxies were modest in size. They did not yet resemble giant spirals or huge ellipticals filled with hundreds of billions of stars. Some were compact, clumpy, and faint enough that finding them pushes our instruments to the limit. Yet their impact was out of all proportion to their size. These small systems helped flood space with light, transform the state of intergalactic gas, and begin the long process of building larger galactic structures through growth and merger. In human history, we often assume the biggest empires matter most. In cosmic history, tiny beginnings can alter everything. That is part of what makes these galaxies so compelling. They were not grand because they were large. They were grand because they arrived early and changed the environment around them. They were among the first engines of transformation in the universe. Their bodies may have been small, but their consequences stretched across cosmic space and deep into cosmic time. Ancient galaxies are not just distant, they are echoes from cosmic dawn. Distance alone would already make these galaxies fascinating, but their real power comes from what that distance means. Because light takes time to travel, the most remote galaxies do not simply sit far away in space. They reach us from an era when the universe was young and the first major structures were appearing. They are echoes from cosmic dawn, preserved not in stone or memory, but in light itself. That gives them a haunting quality. Their signals have crossed almost the entire history of the universe to arrive here now, carrying traces of an age we can never visit directly. When astronomers analyze that faint glow, they are listening to the opening notes of a story that eventually led to the Milky Way, the Sun, Earth, and you. Few topics in science offer that kind of perspective. These galaxies are not remote curiosities. They are surviving witnesses from the beginning, and their ancient light still tells us how the universe first learned to shine. The first galaxies were built from gas almost untouched by heavy elements. At the beginning, the universe was chemically simple. There was plenty of hydrogen, a great deal of helium, and only the faintest trace of anything heavier. That means the first galaxies were assembled from raw material that had barely been processed by stars at all. No rich stew of oxygen, carbon, silicon, and iron yet. Just the basic ingredients left over from the Big Bang, falling together under gravity and beginning the long work of transformation. That simplicity matters, because heavy elements change everything. They help gas cool, condense, and form stars in different ways. Without them, the first galactic systems were operating under harsher rules. Their stars may have formed larger, burned hotter, and lived shorter lives than many stars today. So when we picture the first galaxies, we should not imagine younger versions of modern ones. We should imagine stranger places, built from almost pristine cosmic matter, where the chemistry of the universe was still in its opening act. Many ancient galaxies were smaller than the Milky Way, but fiercely active. Size can be misleading in astronomy. Some early galaxies were far smaller than the vast spiral we live in now, yet they were bursting with energy and change. They packed intense star formation into tight regions, turning gas into starlight at a rate that could make them seem far more dramatic than their modest scale suggests. In human terms, they were less like sprawling empires and more like crowded frontier towns built in a rush. Their gravity was weaker, their structures less settled, and their futures uncertain. But inside them, things were happening fast. New stars flared into existence. Radiation pushed outward. Gas churned and shifted. These systems remind us that power in the universe does not always arrive in giant forms. A galaxy can be small and still blaze with consequence. In fact, the early cosmos may have depended on these compact, vigorous systems more than on any rare giant, because they were numerous, restless, and constantly changing the space around them. Some early galaxies formed stars in brilliant bursts, then quickly changed. Not every galaxy grows at a steady pace. Some seem to live through episodes of sudden brilliance, where star formation surges for a relatively short time and transforms the whole system. In the early universe, that may have happened often. Gas could rush inward, collapse rapidly, and produce a dazzling burst of newborn stars. For a while, the galaxy would shine with extraordinary intensity. Then, the very stars it had created could begin to alter the outcome. Their radiation, stellar winds, and exploding deaths could heat the remaining gas or hurl part of it outward, making future star birth much harder. In that sense, some young galaxies may have raced forward and then slammed on the brakes. Their brightest moments were also the beginning of their next change. That rise and disruption gives them a dramatic quality. They were not calm factories. They were unstable places where creation came in sudden waves, and where one generation of stars could reshape the fate of everything that followed. Ancient galaxies often looked clumpy, messy, and nothing like neat spirals. Modern galaxy photographs can make the universe look elegantly arranged. We see smooth spirals, glowing disks, and graceful forms that appear almost designed. But the early universe was not so polished. Many ancient galaxies seem irregular, broken into bright knots, uneven patches, and distorted shapes that do not resemble the tidy spirals people often imagine. That roughness is a clue to how young they were. Gas was still gathering. Star-forming regions were scattered and intense. Gravity was pulling matter into place, but the job was not finished. These systems were still becoming themselves. If a present-day spiral is like a settled city with avenues and structure, an early galaxy may have been more like a half-built settlement lit by fires, crowded in some regions and unfinished in others. That makes them fascinating to study, because they preserve the universe before symmetry became common. They show us what galaxies looked like while order was still emerging from chaos, and before cosmic architecture had learned its smoother forms. The first galactic collisions began while the universe was still young. Even in the universe's youth, galaxies were not living in splendid isolation. Gravity was already drawing them together, and some of the earliest systems began interacting, tugging, distorting, and colliding long before cosmic history had grown old. This is one of the most dramatic truths about galaxy formation. The first structures had barely arrived, and already they were meeting violently. When galaxies pass near one another or merge, their stars usually do not crash together directly because there is so much empty space between them. but their shapes can be pulled apart, their gas compressed, and their futures permanently altered. New waves of star formation can ignite. Long streams of material can be flung outward. Compact systems can combine into something larger and more complex. So the young universe was not simply a place where galaxies appeared. It was a place where they immediately began changing one another. Growth was social, destructive, creative, and deeply entangled from the very beginning. Some ancient galaxies were already merging before many stars had aged. There is something astonishing about the speed of it. In some corners of the early universe, galaxies may have begun joining together so soon that many of the stars inside them had not even grown old yet. That means merger and assembly were happening almost hand in hand with first-generation growth. A galaxy could still be young in its stellar population and already be caught in the process of becoming part of something larger. This compresses the timeline in a way that feels almost unbelievable. We are used to thinking of big structural change as something that comes later, after long stability. In the early cosmos, stability may have been rare. Some systems were born into crowded environments, where gravity quickly pushed them toward encounters that changed their form, their gas supply, and their pace of star birth. These were not ancient objects sitting quietly in the dark. They were young communities already being folded into larger stories almost before their first light had fully settled. The earliest galaxies glowed strongest in infrared, not visible light. If you could stand near one of the earliest galaxies, much of its light would not seem especially exotic. But by the time that light reaches us, the universe has stretched it. Over billions of years, the expansion of space pulls shorter wavelengths into longer ones, shifting ancient galactic light out of the visible range and into infrared. That is why the earliest galaxies are not mainly found by ordinary optical sight. Their signals have changed on the journey. It is one of the strangest features of cosmology that motion of space itself can rewrite the color of history. What began as energetic starlight arrives as a fainter, redder message that demands different instruments and different eyes. This is also why infrared astronomy feels so powerful. It lets us recover scenes that visible light alone can no longer reveal. In a real sense, the earliest galaxies are still shining across the universe, but the cosmos has hidden them behind a veil of stretched light that only special telescopes can uncover. Dust existed in some young galaxies much earlier than expected. Cosmic dust may sound trivial, like the sort of thing you would wipe from a shelf, but in astronomy, it is one of the great agents of transformation. Dust grains help cool gas, shape new stars, block certain wavelengths, and alter how galaxies appear. For that reason, finding substantial dust in some very young galaxies came as a surprise. Dust has to come from stars. It is made when stellar lives end in violent ways, or when certain aging stars shed material into space. So, if a young galaxy already contains a lot of dust, it suggests that star formation and stellar death had already advanced quickly enough to seed the galaxy with this fine material. That means some early systems were evolving on a startling schedule. Their stars were not only being born. Some had already lived, died, and enriched the galaxy with grains that would affect everything after. Even dust becomes a clue that the young universe may have matured faster and more unevenly than once believed. Ancient galaxies may have recycled gas through winds, outflows, and fresh infall. A galaxy is not a sealed box. Even in the early universe, gas may have been moving in a continual cycle, pulled inward by gravity, blasted outward by stars, and then gathered again for future use. This kind of recycling gives galaxies a far more dynamic life than the simple image of gas turning quietly into stars. Young stars can release fierce radiation and strong winds. Supernovas can drive material away from dense regions and send it streaming into surrounding space. Yet gravity does not stop working. Some of that matter may cool, fall back, and feed later generations of stars. At the same time, fresh gas from the broader cosmic web can keep arriving, replenishing what was lost. So an early galaxy may have breathed in and out like a living system, taking in raw material, expelling it, and drawing new supplies from beyond itself. That sighting helps explain how some galaxies sustained intense activity without exhausting their fuel all at once. Their starlight crossed expanding space, stretching into redder wavelengths as it traveled. When ancient galactic light began its journey, the universe was smaller than it is today. But that light did not travel through a static stage. It moved through space, while space itself was expanding. As the cosmos grew, the light waves were stretched with it, lengthening over time and shifting toward the red end of the spectrum. This is not quite the same as an ordinary moving source changing pitch or color in familiar ways. It is the geometry of the universe leaving its fingerprint on the light. By measuring that stretching, astronomers can estimate how far away a galaxy is and how early in cosmic history its light was emitted. So every redshift measurement is more than a number. It is a clue to age, distance, and the changing scale of the universe itself. The color of ancient galactic light is not simply a property of the galaxy. It is the record of a long journey through a cosmos that kept growing underneath it. Some early galaxies were discovered only because gravity magnified them for us. There are galaxies so distant and faint that even our best telescopes would struggle to see them on their own. Yet the universe sometimes offers help. When a massive object lies between us and a faraway galaxy, its gravity can bend and magnify the incoming light, making the background system appear brighter than it otherwise would. In some cases, that extra boost is the only reason we know the distant galaxy exists at all. Without it, the object would remain buried below the threshold of detection, present in reality but absent from our maps. This gives astronomy a wonderful twist. Gravity is not only a force that shapes galaxies. It can also become part of our observing equipment. Nature provides its own magnifying glass. That means some of the deepest discoveries in cosmic history were not made by technology alone. They required a fortunate alignment of matter, distance, and gravity, turning the universe into an accomplice in revealing its own hidden past. Giant galaxy clusters can act like cosmic lenses for deeper time. A single galaxy can bend light, but a giant cluster of galaxies can do something even more dramatic. These enormous gatherings contain huge amounts of visible matter and far more dark matter, creating gravitational fields powerful enough to distort the light from much more distant objects behind them. In effect, a cluster becomes a vast lens hanging in space. It can brighten remote galaxies, stretch them into arcs, and reveal systems from much earlier times than we might otherwise reach. This turns some galaxy clusters into prized observing targets, not only because they are interesting in their own right, but because they help us peer beyond themselves. Astronomers can use them almost like windows into deeper time. A massive structure in the foreground opens a view onto the young universe behind it. That layered scene is one of the great marvels of cosmology. One ancient system helps us find another, and gravity links them across billions of years in a single act of revelation. A bent arc of light can reveal a galaxy otherwise too faint. Sometimes a distant galaxy does not show up as a neat little dot at all. Instead, its light appears pulled into a curved arc, as though someone has smeared a brushstroke across the sky. That strange shape can be the very sign that tells astronomers something precious is hiding there. The arc is produced when foreground gravity bends the light path from a much more distant source. What matters is not only the distortion, but the fact that the process can make an incredibly faint galaxy visible enough to study. A system that would have vanished into darkness can suddenly announce itself through this warped signature. So a curved streak in a telescope image is not just beautiful. It is evidence that light has taken a detour through a powerful gravitational landscape. Those arcs are like messages folded by the universe itself, and when we learn to read them, they can reveal galaxies from an age so early that ordinary detection might never have found them. Ancient galaxies sometimes appear doubled, smeared, or ringed by lensing. Gravitational lensing does not always create one dramatic arc. Sometimes it produces multiple images of the same distant galaxy. Sometimes it stretches the light into a smear. In especially symmetrical alignments, it can even wrap the light into a near circle called an Einstein ring. These forms can look almost unreal, like visual tricks or errors in the image, but they are some of the clearest examples of gravity shaping what we see. The foreground mass acts like a warped lens, sending light toward us along different paths. That means one remote galaxy can appear more than once in the same field, each image arriving from a slightly different route. For astronomers, this is more than a curiosity. It provides a way to map mass, including dark matter, in the intervening object, and to study background galaxies at greater effective detail. A strange ring, or duplicate image, is therefore a layered event, where one invisible structure helps expose another far behind it. Without gravitational lensing, many early galaxies would still remain invisible. There is a humbling truth hidden in deep-sea astronomy. Some of the earliest galaxies we discuss so confidently are only known because chance alignments allowed their light to be boosted on the way to us. If those foreground masses had not been in exactly the right place, many of these primordial systems would still be beyond our reach. They would exist, they would have shaped cosmic history, and yet we would know nothing about them. Their dependence on lensing reveals how hard the early universe is to study. The first galaxies are not merely distant. Many are intrinsically tiny and faint, their light weakened further by unimaginable travel. It often takes the combined power of modern telescopes and cosmic magnification to bring them into view. So when we admire images of these remote systems, we are sometimes seeing a partnership between human ingenuity and gravitational luck. The universe has hidden some of its earliest chapters well, and lensing is one of the rare ways it lets us read them. Webb can separate tiny ancient galaxies that once blurred together. Before sharper infrared vision arrived, some of the faintest distant sources looked like little more than smudges. Astronomers could tell something was there, but not always whether it was one galaxy, several crowded together, or a more complex arrangement of structures. Webb has changed that. Its sensitivity and resolution allow it to distinguish tiny ancient systems with far greater clarity, pulling apart what once seemed merged into a single blur. This matters because confusion in the image can lead to confusion in the story. A source that appears unusually bright or massive might turn out to be several smaller galaxies packed close together. Once separated, each one tells a more accurate tale about early cosmic structure. That shift from blur to detail is one of the great pleasures of new astronomy. It shows that deeper seeing does not only reveal more objects, it also reveals the true character of objects we already thought we understood, sharpening the earliest universe into a much more intricate place. Some distant smudges turned out to be several galaxies crowding together. In the earliest deep observations, a faint patch of light could seem like one object simply because our view was not sharp enough to say otherwise. But as imaging improved, some of those remote smudges began to break apart into separate galaxies packed closely in the same region. That discovery changes the feeling of what we are looking at. Instead of one lonely beacon in the dark, we may be seeing a crowded environment where multiple small systems are gathering, interacting, and perhaps preparing to merge. It also means that early brightness can sometimes come from company rather than from one extraordinary source. This is important for understanding how structure formed. The young universe may have been knitting itself together through clusters of small galaxies, rather than relying only on isolated rapid giants. In practical terms, better resolution lets astronomers avoid being fooled. In emotional terms, it replaces solitude with community, showing that even in the distant past, some galaxies were already growing up in busy neighborhoods. Ancient galaxies often lived in neighborhoods where future galaxy clusters were forming. The earliest galaxies did not all emerge in the same kind of environment. Some formed in regions that would later become ordinary settings. Others appeared in especially dense neighborhoods where matter was already gathering into what would one day be full galaxy clusters. These crowded areas are sometimes called protoclusters, and they are among the most exciting places to study in the early universe. They let astronomers witness not just the birth of galaxies, but the beginnings of much larger cosmic communities. A young galaxy in such a region is part of the developing social structure. Nearby companions, shared gas flows, and strong gravitational influences can all affect how it grows. So location matters even on the grandest scale. A galaxy's surroundings can shape its future long before that future arrives. When we find ancient galaxies in these forming clusters, we are not simply finding isolated relics. We are catching the first assembly of cosmic cities, where entire populations of galaxies were starting to gather. A galaxy seen early can become a whole family tree later. One of the most remarkable ideas in astronomy is that a single early galaxy is not only an object in its own right. It can be the starting point of a long line of descendants. Through mergers, accretion, and ongoing star formation, one small system can contribute to several later structures, while larger galaxies can absorb many such ancestors into themselves. This means a galaxy glimpsed in the early universe is not frozen in significance. It may become part of a branching family history that extends across billions of years. Some of its stars might end up in the halo of a larger galaxy. Some of its gas might help form later generations elsewhere. Some of its structure may be erased entirely while its material survives. That is why galaxy evolution feels so rich. We are not looking at separate cast members entering and leaving the stage. We are watching lineages unfold. A faint early system can become an ancestor with countless descendants written into the later universe. Some primeval galaxies may be the ancestors of today's giant ellipticals. The giant elliptical galaxies we see today can look old, smooth, and almost stately, but their beginnings may have been far more chaotic. Some primeval systems in the early universe could be the rough ancestors of these modern giants, caught during phases when they were compact, gas-rich, and rapidly assembling mass. Over time, repeated mergers and intense bursts of star formation may have transformed them into the large, rounded galaxies now found in the hearts of rich clusters. That possibility is thrilling because it links two very different cosmic moods. The unruly young universe may have produced the seeds of the calmest giants we know. Beneath the smooth appearance of a present-day elliptical may lie a buried story of collisions, compression, and early violence. So, when astronomers search for distant ancestors of these giants, they are trying to reconstruct a long metamorphosis. They want to know how something messy, crowded, and formative in the beginning became one of the most massive and settled structures in the mature universe. The first stars inside galaxies were probably hotter and shorter-lived than ours. The earliest stars were likely born under conditions far more extreme than those of the Sun. The gas around them had almost none of the heavier elements that help modern clouds cool and fragment into many smaller stars. Without that cooling, gravity may have built stars of enormous mass, blazing blue-white and ferociously hot. A star like that does not drift through a calm, patient life. It burns through its fuel with astonishing speed and dies young. Some may have lived only a few million years before ending in violent collapse or explosion. That means the first galaxies may have been lit by stellar populations very different from the ones we know best today. Their skies would have been harsher, brighter, and more intense. These vanished stars no longer shine for us directly, but their brief lives may have set the whole early universe on a new course, flooding it with radiation and beginning the first great chemical transformations. Ancient galaxies made the first heavy elements that later built planets. The early universe did not begin with the ingredients for rocky worlds. There was no iron for a planet's core, no silicon for stone, no calcium for bone, and no phosphorus for living cells. Those had to be made. Ancient galaxies were where that long alchemy truly began. Inside their stars, lighter elements were fused into heavier ones. When those stars died, they scattered their new material back into space. That enriched gas then became the raw matter for later generations of stars, and eventually, planetary systems. Every world with mountains, minerals, and solid ground depends on that process. In a very real sense, planets are second-hand creations, built from the remains of earlier stellar lives. So when we look at ancient galaxies, we are not only looking at distant light. We are looking at the first workshops that made rocky existence possible. Long before Earth formed, those early systems were preparing the chemistry that would one day allow worlds to harden from dust. Every atom of carbon in you began in ancient stellar furnaces. Carbon feels intimate because it is the backbone of life as we know it. It is in your cells, your breath, your skin, and the molecules that carry memory and energy through your body. Yet none of it existed at the beginning. The early universe had no storehouse of carbon waiting to be used. It had to be forged inside stars. Deep in their hot interiors, helium nuclei were driven together under immense pressure until carbon formed. Later, when those stars shed their outer layers or died, that carbon escaped into space and joined the raw material of future stars, planets, and living things. This means your body contains matter that was born in stellar interiors long before the sun. The thought is astonishing because it collapses the distance between biology and cosmology. You are not simply living in a universe made of stars. Part of you is the result of ancient stellar creation, carried across cosmic history until it could become life. Early galaxies forged oxygen long before Earth ever existed. When people think about oxygen, they usually think about breathing, forests, or oceans. But oxygen's story begins much earlier and much farther away. It was created inside stars in ancient galaxies, where nuclear fusion built it from lighter elements and then released it back into space when those stars died. That means the oxygen in Earth's rocks, water, and air was not invented here. It was inherited from much older stellar generations. In the early universe, every atom of oxygen had to be made for the first time. Some of the first galaxies were among the places where that work began in earnest. They forged the element that would later help shape planetary crusts, fill seas, and support animal life. There is something deeply moving in that. The oxygen you breathe every day is part of a story that began in galaxies so remote that their light still struggles across the universe. Breath itself is tied to cosmic ancestry. Iron became common only after generations of stars had already lived. Iron is often treated as a symbol of strength and permanence, but in cosmic history it arrived relatively late. Lighter elements such as carbon and oxygen could be made earlier in stellar interiors, yet large amounts of iron required repeated rounds of stellar birth and death. It built up gradually as generations of stars lived, fused, exploded, and enriched their surroundings. That means the first galaxies were not immediately rich in iron. They had to earn it over time through cycles of creation and destruction. This makes iron a kind of historical marker. When astronomers detect more of it, they are often seeing evidence that a galaxy has already passed through multiple chapters of stellar evolution. It has a deeper past than its age alone might suggest. The iron in your blood and in the core of Earth is therefore part of a long-delayed inheritance. It comes from a universe that needed time, repetition, and many lost stars before this one heavy element became truly common. Ancient galaxies were chemical workshops, not just islands of light. A galaxy can look simple from a distance, just a remote glow suspended in darkness, but that appearance hides a much richer reality. Inside ancient galaxies, matter was being transformed from one state into another through countless stellar lives. Gas clouds collapsed into stars. Stars fused new elements in their cores. Explosions and winds spread those elements back into space. New clouds formed from the enriched debris, ready to begin again. So these early systems were not passive collections of light. They were active chemical engines, changing the composition of the universe with every generation. Their importance lies not only in how they looked, but in what they made possible. They turned a simple cosmos into a more varied one. They produced the ingredients for later planets, atmospheres, oceans, and life. Seen this way, an ancient galaxy is less like a distant ornament and more like a vast workshop, where the raw material of the young universe was steadily being remade into future complexity. Some young galaxies already held surprising amounts of enriched gas and dust. A galaxy can seem young by age and still carry signs of a surprisingly eventful past. In some early systems, astronomers have found gas and dust that already appear chemically enriched, which means earlier rounds of stars had already altered the galaxy's material. That is a startling clue, because enrichment takes time and violence. Stars must form, live, and then return processed matter to space. Dust must condense from stellar ejecta and survive long enough to become part of the galactic environment. When those features show up early, they suggest that some galaxies were racing through their development. Their youth was deceptive. Beneath the label of young galaxy was a place where multiple stellar generations may already have come and gone. That makes these systems feel unexpectedly seasoned, as if we arrived near the beginning and found traces of history already layered into the air. Even their dust becomes evidence that the early universe was not uniformly primitive or slow. Their earliest supernovas may have reshaped whole galaxies in violent waves. When a massive star explodes as a supernova, it does far more than mark the end of one life. It releases energy on a scale so vast that it can blast surrounding gas outward, heat whole regions, and alter the future of star formation around it. In a small early galaxy, that effect may have been even more dramatic. One or several powerful explosions could have sent shockwaves through much of the system, stirring gas, compressing some clouds, and driving other material away entirely. That means the first supernovas in ancient galaxies were not isolated events. They may have acted like turning points in galactic history. They could trigger new births in one region while starving another. They could spread heavy elements across wide areas and change the chemistry of future generations. In a modern, large galaxy, one explosion may be a local drama. In a young, compact one, it may have been something closer to a civic event, felt across the whole galactic body. Ancient galaxies likely lost gas easily because their gravity was weaker. Many early galaxies were small, and that gave them a problem. Their gravity was not always strong enough to hold onto all the gas that stars and explosions stirred up. When intense radiation, stellar winds, or supernovas pushed material outward, some of it may simply have escaped into intergalactic space. That matters because gas is a galaxy's future. It is the fuel for later generations of stars. Lose too much of it, and growth slows or even stalls. So in the early universe, some galaxies may have lived in a precarious balance, trying to build themselves while also shedding the very matter they needed to continue. This makes their story feel more fragile than the word galaxy might suggest. We often imagine galaxies as vast and secure. Some of the earliest ones may have been more vulnerable, bright little systems trying to hold themselves together against the consequences of their own activity. Creation inside them could also become a kind of loss. The smallest early galaxies may have struggled to hold onto their stars. Gas was not the only thing young galaxies could lose. In the smallest systems, even stars might have been vulnerable to being stripped away by outside forces or internal instability. A weak gravitational grip means a close encounter with another galaxy, or the pull of a larger nearby structure, can tug stars into long streams and leave the original system diminished. Over time, this can hollow a galaxy out or even erase much of it as a distinct object. In the early universe, where interactions were common and environments could be crowded, some tiny galaxies may have had a hard time keeping their own members. That idea gives them a poignant quality. They were trying to become enduring homes for stars while living in a cosmos that kept disturbing them. Some may have survived only as fragments, their stars later absorbed into larger galaxies. So, when we study galactic growth, we are not only studying success. We are also tracing the remains of systems that could not keep hold of themselves. Some ancient galaxies were so compact they resembled crowded cosmic embers. Not every galaxy spreads its light across a wide, elegant disk. Some ancient systems appear extraordinarily compact, with tremendous activity packed into very small regions. They were dense, bright, and crowded, as though the energy of a much larger galaxy had been compressed into something tighter and more intense. That gives them a striking emotional texture. Instead of imagining a broad city of stars, imagine a glowing ember, small in outline, but burning fiercely at the center. In such places, stars formed close together, radiation filled nearby space, and the consequences of each stellar generation may have been felt quickly across the whole system. These compact galaxies are fascinating because they show that galactic size and galactic intensity do not always rise together. A system can be small in scale, yet astonishingly powerful in effect. They suggest that the early universe sometimes built with concentration rather than grandeur, producing tight little furnaces whose influence reached far beyond their modest boundaries. A young galaxy could pack enormous activity into a surprisingly tiny space. Picture a region much smaller than the Milky Way, yet alive with furious star birth, energetic radiation, and gas moving in complex patterns. That is the kind of scene some young galaxies may have hosted. Their compactness did not make them quiet. In fact, the limited space may have made everything feel more immediate. New stars could flood nearby gas with light. Explosions could influence the whole system more easily. Dense pockets of matter could interact on shorter timescales. The result is a galaxy that feels less like a sprawling continent and more like a crowded forge, where many transformative events happen within a confined area. This challenges our instinct to associate greatness with scale. In cosmic history, tiny spaces can hold astonishing intensity. A young galaxy did not need to be huge to matter. It only needed enough fuel, enough gravity, and the right conditions for a burst of concentrated activity. Some of the earliest major dramas in the universe may have unfolded in places surprisingly small. The earliest galaxies may have looked more like knots than pinwheels. When people imagine a galaxy, they often picture sweeping spiral arms turning in a beautiful, organized disk. But the earliest galaxies may have looked nothing like that. Many were probably irregular clumps of stars and gas, dense knots where matter had gathered without yet settling into smooth, large-scale structure. Their appearance may have been more tangled than graceful, more like bright stitched patches than cosmic pinwheels. That roughness tells us something important. Order in the universe had to be built. It was not present from the start. The neat visual forms we admire in later galaxies were the result of long processes of settling, rotation, merger, and growth. Before those processes had time to work, the first systems may have looked almost unfinished. That does not make them less interesting. It makes them more revealing. They show us the universe before its architecture was refined, when galaxies were still emerging from knots of matter and had not yet learned the elegant shapes we now associate with them. Spiral arms were not the universe's first idea of a galaxy. Spiral galaxies feel iconic because they are so visually striking, yet they represent a more mature stage of structure than many people realize. The earliest galactic systems were likely irregular, compact, and turbulent, rather than organized into long, graceful arms. Spiral structure seems to require time, rotation, and a certain level of dynamical settling before it becomes prominent. In other words, the universe did not begin with pinwheels. It began with rougher forms that only later evolved into those familiar shapes. This matters because it reminds us that beauty in astronomy often has a history. What seems timeless is actually the result of development. A spiral galaxy is not the first sketch. It is a later draft. So when we look at ancient galaxies, we are seeing the cosmos before one of its most famous visual styles had fully emerged. That makes the early universe feel more experimental, as though it was trying out different arrangements before arriving at the elegant structures that now fill so many telescope images. Smooth, grand-designed spirals came much later than the first galactic systems. Those majestic spiral galaxies with clear, sweeping arms and balanced forms are not the opening chapter of the universe. They belong to a later, more settled era. To build a smooth, grand designed spiral, a galaxy needs enough time for its disk to organize, for its motions to become more coherent, and for large-scale patterns to emerge and persist. The earliest galactic systems were often too young, too disturbed, or too compact for that kind of symmetry. They were still gathering matter, experiencing collisions, or living with intense turbulence. So the grand spirals we admire today are the products of long cosmic patience. They are what happens after ages of motion, cooling, and structural refinement. There is something beautiful in that delay. The universe's most elegant galactic forms were not instant triumphs. They were achievements. When we study ancient galaxies, we are looking back before those achievements existed, at a time when structure was still rough and the familiar visual calm of later spirals had not yet arrived. Ancient galaxies often grew from fragments joining, not from perfect order. Galaxies did not always begin as unified, elegant systems. In many cases, growth may have happened through pieces coming together, small clumps of matter, pockets of stars, and gas-rich fragments gradually merging into something larger. This kind of assembly is messier than the image of one cloud collapsing neatly into one stable galaxy. It suggests a universe where structure was built by gathering and rearranging, not by simple orderly design. The result would have been galaxies with uneven shapes, multiple bright regions, and traces of past joining written into their motions and composition. That is a deeply compelling picture because it makes galaxy formation feel almost architectural. Blocks of matter came together under gravity, sometimes smoothly and sometimes violently, until larger systems emerged. The mature galaxy was not always present in miniature from the start. Sometimes it had to be built from pieces. This means that ancient galaxies preserve not only youth, but construction history, the scars and seams of a cosmos assembling itself from fragments. Some early galaxies may have rotated, while others were mostly turbulent. Rotation is one of the great organizing forces in astronomy. Given enough time, it can help shape a disk and bring some order to a galaxy's motions. But in the early universe, not every system seems to have reached that point. Some ancient galaxies may already have shown signs of coherent rotation, while others were dominated by turbulence, with gas and stars moving in more chaotic patterns. That contrast is revealing. It means the early universe was not producing one standard type of galaxy on one schedule. Different systems could be at very different stages of organization, even within roughly the same era. One might be beginning to settle into a rotational structure. Another might still be roiled by inflowing gas, recent mergers, or intense feedback from star formation. This variety makes early galaxies especially interesting to study. They are not merely old. They are snapshots of different experiments in galactic becoming, some leaning toward order, others still living in a more chaotic and unsettled state. Gas in young galaxies likely churned faster than gas in calmer modern ones. The gas inside a modern, well-settled galaxy can move in relatively ordered ways, especially in stable rotating disks. In young galaxies, the situation was probably far rougher. Gas may have churned with higher speeds, stronger turbulence, and more abrupt changes in direction as matter streamed inward, stars formed in dense bursts, and explosions pushed energy back into the system. That restless motion would have shaped everything. It could influence where stars formed, how quickly they formed, and whether the galaxy settled into a disk or stayed irregular for longer. In a sense, the gas was the weather of early galactic life, and the forecast was often stormy. This makes ancient galaxies feel less like static objects and more like dynamic environments. Their visible light came from stars, but much of their fate depended on the unruly behavior of the gas between them. To understand those young systems, you have to imagine not stillness, but ceaseless motion inside them, from edge to edge. Ancient galaxies were built in motion, noise, and gravitational unrest. It can be tempting to picture the early universe as silent and majestic, but the true story was far more unruly. Ancient galaxies were being assembled in a setting of constant movement. Gas flowed in from the cosmic web. Stars ignited and exploded. Small systems merged. Gravity pulled, stretched, and rearranged matter on every scale. If we could translate those processes into human senses, the early universe would feel less like a museum and more like a construction site of enormous power. The first galaxies were not born finished. They were built amid disturbance, with every gain in structure shaped by motion and tension. That matters because it changes how we see cosmic beauty. The grand forms of later galaxies emerged from unrest, not from calm beginnings. Ancient galaxies carry the drama of becoming. Their light may reach us in silence, but the worlds that produced it were shaped by activity, upheaval, and relentless gravitational negotiation from the moment they first began to gather. The first galaxies were less polished, but often more intense. Early galaxies may not have had the smooth shapes and settled grandeur of later cosmic systems, but in many cases, they made up for that with sheer intensity. They were more compact, more chaotic, and often more active in relation to their size. Star formation could proceed at striking rates. Radiation fields could be fierce. Structural change could happen quickly through bursts, mergers, or gas flows. So while they lacked the visual polish of mature spirals and giant ellipticals, they may have felt far more dramatic from the inside. There is something wonderfully human about that contrast. Youth is not always graceful, but it can be vivid. The same may be true on galactic scales. The first galaxies were rough drafts of later beauty, yet they were also places of extraordinary creative power. They remind us that the universe's earliest structures were not faded beginnings. They were bright, unstable, high-energy environments where much of cosmic history was being set in motion for the first time. Some early galaxies may have hosted quasars brighter than entire star cities. In some of the earliest reaches of cosmic history, a single point at the galaxy's center may have shone with such force that it overwhelmed the combined light of billions of stars. That point was not a star at all. It was a quasar, powered by matter spiraling into a ravenous black hole. As gas fell inward, it heated to extraordinary temperatures and blazed across space with terrifying brilliance. For a time, the core could become more luminous than the rest of the galaxy around it. This gives some young galaxies a strange identity. They were not merely homes to stars. They were stages for central engines so bright they could dominate the whole performance. When astronomers detect one of these ancient beacons, they are seeing not a calm city of starlight, but a place where gravity has turned hunger into radiance. It is one of the most extreme ways the young universe announced itself across the dark. A feeding black hole can outshine the galaxy wrapped around it. A black hole is often imagined as darkness itself, yet the brightest thing in a galaxy can sometimes be the region just outside one. The black hole does not glow. The infilling matter does. As gas and dust whirl inward, they form a blazing disk that becomes hotter and brighter as it approaches the point of no return. Friction, compression, and magnetic forces turn that descent into one of the most efficient light-making processes in the universe. The result can be astonishing. The central engine becomes so brilliant that the surrounding galaxy, with all its stars, fades into relative insignificance. This reverses our intuition. We expect the galaxy to be the main event and the black hole to be hidden inside it. Sometimes the opposite is true. The galaxy becomes almost a supporting structure for the luminous fury at its heart. In the early universe, that imbalance may have been especially dramatic, making some galaxies look like halos around a single act of gravitational fire. Ancient quasars prove giant black holes appeared astonishingly early in cosmic history. Quasars from the young universe are not just bright curiosities. They are evidence for something deeply puzzling. To power one of these ancient lighthouses, a black hole must already have grown to immense size, sometimes reaching hundreds of millions or even billions of solar masses. The problem is time. In the early universe, there does not seem to have been much of it. These monsters appear when cosmic history was still in its youth, which means their growth had to begin very early and proceed with startling efficiency. They force astronomers to confront a difficult question. How did such enormous objects appear so soon after the first galaxies began to form? That is why ancient quasars matter so much. They are not merely signs of powerful galactic centers. They are proof that giant black holes were already present when the universe was still young enough to make that seem almost unreasonable. Their existence alone turns early cosmic history into a mystery story. No one fully knows how some early black holes grew so quickly. This is one of the great unresolved dramas of modern astronomy. Black holes in the young universe seem to have reached enormous masses on timescales that strain many standard models. One possibility is that they began from unusually massive seeds, perhaps formed when huge clouds of gas collapsed directly, instead of first becoming ordinary stars. Another is that they fed at extraordinary rates, gulping down matter almost continuously, with very little interruption. There may also be cases where mergers help them grow faster. The trouble is that none of these explanations has settled the matter completely. Each solves part of the puzzle while raising new questions. That uncertainty is what makes the problem so compelling. We are not looking at a small discrepancy. We are looking at objects whose very existence suggests that the early universe may have had pathways to rapid growth that we still do not fully understand. Some of its first monsters seem to have learned how to grow before we learned how to explain them. Webb has found young galaxies with actively growing black holes inside. One of the most exciting powers of Webb is that it can peer into the early universe and catch galaxies in the act of becoming. In some of those young systems, astronomers have found signs that the central black holes are not dormant relics. They are actively feeding. Their presence is revealed through distinctive light, energetic emission, or other clues that matter is falling inward and releasing huge amounts of energy. This matters because it shows that black hole growth was not confined to rare gigantic quasars alone. Even in comparatively young galaxies, central black holes may already have been hard at work, building mass while the galaxy itself was still assembling stars and structure. That creates a much richer picture of early cosmic life. Growth was happening on more than one front at once. A galaxy was not simply making stars and waiting for its center to awaken later. In some cases, the heart was already active, changing the story while the rest of the system was still taking shape. Ancient galaxies may have grown alongside black holes from the very beginning. For a long time, it was tempting to imagine galaxy growth and black hole growth as related but partly separate stories, with one perhaps following the other. Increasingly, the early universe suggests something tighter. Some galaxies and their central black holes may have been developing together from remarkably early times, each influencing the other as both accumulated mass. Gas flowing inward could feed star formation across the galaxy, while also supplying the central region. At the same time, energy released near the black hole could alter the surrounding gas, changing how easily future stars could form. This turns a galaxy into more than a home with something interesting at the center. It becomes a partnership, or perhaps a rivalry, between two modes of growth. The stars build the visible body. The black hole deepens the invisible center. In ancient galaxies, these two processes may have been intertwined almost from the start. The earliest galactic history may therefore be impossible to understand fully unless we follow both stories at once. A black hole in a tiny early galaxy can challenge giant theories. There is something especially provocative about finding a substantial black hole inside a very small young galaxy. On paper, it seems almost disproportionate, as though a modest little system has somehow acquired a central engine too large or too active for our expectations. That mismatch matters because many theories link black hole growth closely to the mass and development of the host galaxy. A surprisingly important central black hole in a tiny system suggests that those relationships may have formed unevenly, or that black holes sometimes got a head start. It raises the possibility that in some cases, the center matured faster than the surrounding galaxy. That would reshape how we think about the earliest stages of cosmic structure. Instead of large galaxies producing large black holes in a tidy pattern, the young universe may have allowed stranger combinations. A small galaxy with an outsized dark heart becomes more than an oddity. It becomes a test of whether our biggest theories can survive one very unsettling little example. Some early galaxies may hide black holes behind thick veils of dust. Not every growing black hole announces itself with a blinding beacon. In some young galaxies, the central region may be wrapped in so much dust and gas that the activity is partly hidden from ordinary view. The feeding is still happening. Matter is still falling inward. Energy is still being released. But much of the most obvious light is absorbed, reprocessed, or blocked by the surrounding material. This means the early universe may contain more active black holes than we first realized, with some concealed inside galaxies that look far less dramatic at first glance. That hidden population is important because it changes the census of early growth. We may be missing major actors simply because they are veiled. It also adds a wonderful sense of secrecy to these galaxies. Beneath dusty outer layers, a powerful central engine may be working furiously, shaping the future while staying partly out of sight. Some of the young universe's most important transformations may have happened behind curtains. The universe made monsters early, and ancient galaxies had to live with them. There is no softer word for some of these objects. The early universe produced black holes of extraordinary scale and appetite, and young galaxies had to build themselves in their presence. These were not gentle companions. A fast-growing central black hole could flood surrounding regions with radiation, drive winds outward, and alter how gas behaved across the galaxy. In some cases, it may have helped regulate growth by heating or expelling material that would otherwise form new stars. In others, it may have compressed gas in ways that stirred fresh activity. Either way, its presence meant that a galaxy's life was being shaped by something extreme lodged at its heart. That gives ancient galaxies a more dangerous and dramatic atmosphere than people often imagine. They were not just nurseries of stars. Some were places where ordinary galactic building had to proceed under the influence of central monsters, powerful enough to affect the fate of everything around them while remaining dark at the core. Young galaxies were nurseries, but also battlegrounds for gravity and radiation. The early universe was creative, but it was not peaceful. Young galaxies brought stars into existence in large numbers, which makes them true nurseries. Yet the same processes that created light also unleashed forces that could tear at the very material needed for future growth. Gravity pulled gas inward and tried to gather it into denser regions. Radiation from hot young stars pushed outward. Supernovas hurled energy into surrounding clouds. Black holes added their own influence in some systems, stirring and heating the galactic environment. So a young galaxy was often a contested place, where creation and disruption happened together. Gas might collapse in one region while being blown apart in another. One generation of stars could clear the ground beneath the next. This tension is part of what makes ancient galaxies so fascinating. They were not serene places waiting to mature. They were active arenas where opposing forces were constantly negotiating the future. The beauty of galactic birth came intertwined with struggle. Reionization began when early galaxies flooded space with powerful ultraviolet light. After the universe cooled from its earliest hot state, space was filled with neutral hydrogen gas that could trap energetic light. For the cosmos to become transparent across great distances, that hydrogen had to be broken apart again. Early galaxies helped start that transformation. Their hot young stars produced powerful ultraviolet radiation that streamed outward into surrounding space. When enough of that light escaped each galaxy, it began stripping electrons from hydrogen atoms in the intergalactic medium. This process is called reionization, and it marks one of the great turning points in cosmic history. The universe was not merely forming stars and galaxies for their own sake. Those early systems were changing the condition of space itself. Their light reached beyond their boundaries and began remaking the wider cosmos. It is extraordinary to realize that some of the first galaxies were not just visible objects in the dark. They were active agents in a universal transition, helping transform a murky young cosmos into one more open to light. Ancient galaxies slowly cleared the hydrogen mist left after the Big Bang. Imagine the early universe not as empty blackness, but as a vast landscape filled with a thin cosmic mist. That mist was neutral hydrogen spread through intergalactic space, and it made the young cosmos much harder for energetic light to cross. Ancient galaxies began changing that condition. Their stars sent radiation outward that started clearing the mist around them. The process was gradual and local at first. A galaxy would brighten its surroundings, creating a patch of more transparent space. Over time, more galaxies did the same, and the cleared regions expanded. This gives early cosmic history a beautiful texture. The universe did not become transparent everywhere at once. It was opened little by little by sources of light embedded within it. These galaxies were like distant lanterns whose glow did not merely illuminate the fog. It transformed the fog itself. Their influence extended far beyond their visible bodies, helping convert a young, obscured universe into one where light could travel freely across immense distances. The young universe was once opaque, even though light already existed. That sounds almost contradictory at first. How can light exist, and yet the universe still be opaque? The answer lies in the matter filling early space. Even after the first light sources had begun to shine, much of the cosmos remained filled with neutral hydrogen that absorbed or scattered energetic radiation. So light was present, but long-range visibility had not yet been achieved. A star could blaze within its own environment, while the wider universe still remained murky to certain wavelengths. This is one of the strangest features of early cosmic history. Darkness was not simply the absence of light. It was often the problem of transmission. The universe had luminous sources, but the medium between them had not yet been transformed enough to let their light travel freely across great expanses. That gives reionization a special importance. It was not about creating light from nothing. It was about making the cosmos transparent enough for that light to truly connect distant regions of space. It took countless early galaxies to make intergalactic space transparent. No single galaxy could finish the job alone. Reionization was a collective achievement written across the early universe by enormous numbers of young systems. Some were bright and dramatic. Many others were likely faint, small, and much harder to detect today. Together, their radiation gradually changed intergalactic hydrogen from a neutral fog into a more transparent medium. This is one of the most stirring ideas in cosmology. The universe did not open through one grand act by one dominant source. It cleared through the combined efforts of vast populations of galaxies, each contributing a little to a transformation far larger than itself. That collective power matters because it means even modest galaxies may have played crucial roles in one of the biggest transitions in cosmic history. Their individual light was limited. Their shared effect was enormous. Transparency on a universal scale may have depended not on the brightest few alone, but on the gathered output of countless early star cities working together across the dark. Some ancient galaxies carved clear bubbles through the cosmic fog around them. As radiation escaped from young galaxies, it did not clear all of space at once. It first created local zones of change around each source, regions where neutral hydrogen had been ionized and the surrounding medium became more transparent. You can think of these as clear bubbles opening inside a much foggier universe. Each early galaxy sat inside or near one of these expanding zones, pushing outward as more energetic light streamed into the intergalactic medium. The image is wonderfully vivid. The young cosmos was not transformed by a flat wave sweeping across it. It was punctured by growing islands of clarity. Around each active galaxy, light won a little territory. Those bubbles mattered because they shaped what could be seen, how radiation traveled, and how neighboring systems began to interact through their expanding regions. A galaxy in the early universe was therefore doing more than shining. It was clearing room around itself, carving out a pocket of openness in a cosmos still largely wrapped in haze. Those bubbles later grew, overlapped, and transformed the universe for good. At first, the cleared zones around early galaxies were separate. One galaxy opened its own region. Another did the same somewhere else. But as more sources appeared and existing ones kept radiating, those bubbles expanded until they began to meet. Once that happened, the process accelerated in significance. Separate pockets of transparency linked together into larger transparent domains, and eventually vast portions of the universe became open to energetic light. This overlap marks one of the great phase changes in cosmic history. The patchy transformation became a connected one. The cosmos crossed from local clearing to large-scale transparency. There is something almost organic about the image, as though many points of light were each opening a little wound in the fog until the whole darkness tore apart. After that, the universe was never the same. The medium between galaxies had been fundamentally altered. Their bubbles did not merely expand. Together, they changed the long-term optical character of the cosmos for everything that came after. We may be seeing galaxies that helped end the cosmic dark ages. The phrase cosmic dark ages sounds dramatic, and it is. It refers to the long interval after the universe first became neutral and before enough stars and galaxies existed to flood it with transformative light. During that era, there were no mature galaxies lighting up the cosmos as we know them now. Then, the first luminous systems began to appear. Some of the distant galaxies we detect today may be among the populations that helped bring that dark chapter to a close. Their stars, their radiation, and their growing structures contributed to a transition from obscurity to illumination. That makes them far more than remote astronomical targets. They are participants in one of the greatest turning points the universe ever experienced. When we detect one of these faint ancient systems, we may be catching sight of a source that was present as the cosmic night began to lift. It is hard to imagine a more arresting role for a galaxy than that. Ancient galaxies changed not only themselves, but the space between them. Most objects in the universe affect their own internal condition. Ancient galaxies did that, of course, by forming stars, building structure, and enriching their gas. But they also did something more expansive. Through radiation and energetic outflows, they influenced the medium beyond their visible edges. Their existence altered the state of intergalactic space. This is one of the most profound facts about the early cosmos. A galaxy was not merely a self-contained island. It was a source whose actions reached into the vastness between other galaxies, modifying how light traveled and how hydrogen behaved over enormous scales. That means the story of ancient galaxies cannot be told only by looking inward. Their importance lies partly in what they did to their environment. They changed not just their own future, but the conditions in which other galaxies would later live. In the early universe, the space between things was not passive emptiness. It was a frontier that galaxies themselves helped transform. The faintest young galaxies may have done the most clearing work. This is one of the great cosmic ironies. The galaxies easiest for us to notice are often the bright exceptional ones, yet the heavy lifting of reionization may have been done largely by far smaller and fainter systems. If such galaxies were numerous enough, their combined ultraviolet output could have outweighed that of the rare giants. Individually, they were modest. Collectively, they may have been decisive. That possibility is thrilling because it shifts the spotlight away from the obvious stars of the show and toward the hidden crowd. The early universe may have become transparent not because of a few dazzling galaxies alone, but because vast numbers of small ones quietly filled space with transformative light. It is a humbling lesson in scale and numbers. The brightest beacon is not always the main architect of change. In cosmic history, countless faint galaxies that we can barely glimpse today may have been the ones that truly opened the universe and carried it out of its murkiest age. Cosmic dawn was not one switch, but a slow brightening by galaxies. It is tempting to imagine the beginning of visible cosmic history as a sudden moment, a single dramatic instant when darkness ended and light took over. The real story appears gentler and far more interesting. Cosmic dawn was a drawn-out transition. Galaxies formed at different times in different environments with different strengths. Their radiation spread unevenly. Clear regions emerged, expanded, and eventually merged. Some areas brightened earlier than others. The darkness lifted in stages. That slow brightening gives the early universe a more textured and beautiful history. Instead of a single switch being flipped, the cosmos gradually woke up through the accumulated work of many galaxies across time. This means dawn on the largest scale was still a dawn in the familiar sense. It was progressive, uneven, and full of changing light. The universe did not leap all at once from obscurity to clarity. It brightened by degrees, and galaxies were the ones that carried morning outward through the dark. Some ancient galaxies appear older than early models once predicted. When astronomers first began imagining the earliest galaxies, many models suggested that the young universe should produce systems that were small, raw, and only lightly developed. Then, observations began turning up galaxies whose light hinted at something more advanced. They seemed brighter, more structured, or more chemically evolved than expected for such an early moment in cosmic history. That does not mean they were literally older than the universe allowed. It means they looked more mature than some theories had prepared us to see. In a way, they gave the impression of arriving early to their own story. That is what makes them so gripping. They force astronomy to ask whether the universe assembled complexity faster than we thought, or whether our first impressions of these galaxies sometimes exaggerate their maturity. Either way, the effect is the same. We look into cosmic youth and find systems that seem to carry more history than expected, as though the universe learned some of its hardest lessons unusually fast. Webb forced astronomers to rethink how quickly galaxies could assemble. Before Webb began sending back its deepest views, many researchers expected the first substantial galaxies to emerge in a slower and more cautious progression. Then the telescope opened a wider and sharper window onto the early universe. Suddenly, astronomers were looking at objects that seemed unexpectedly luminous and organized at very early times. That forced a change in mindset. Perhaps gas gathered faster. Perhaps star formation surged harder. Perhaps the first dark matter halos built structure more efficiently than expected. Or perhaps several effects combined in ways earlier models had underestimated. This is one of the most exciting moments in science, when better evidence does not merely fill in details, but changes the tempo of the story itself. Webb did not just reveal more young galaxies. It made astronomers reconsider how rapidly the cosmos could go from near simplicity to visible structure. The early universe began to look less like a slow rehearsal and more like a swift, high-pressure opening act. A surprisingly bright early galaxy can unsettle years of simulations. Computer simulations are one of astronomy's great tools. They let researchers test how galaxies might grow, merge, light up, and evolve under known physical laws. But all of that careful work can be rattled by one stubborn object. If a very early galaxy appears much brighter than expected, it raises difficult questions. Is the galaxy forming stars at an extreme rate? Is its light being boosted by a hidden black hole? Are several galaxies blending together in the image? Or has the model simply missed an important pathway in early cosmic growth? That is why a single bright source can matter so much. It does not merely sit there as an oddity. It presses against assumptions built into years of theoretical work. In science, surprise is not a nuisance. It is often the point where understanding deepens. A bright early galaxy can become a kind of test flare, illuminating the places where our simulations still need to become more faithful to the universe they are trying to imitate. Ancient galaxies are testing whether our galaxy formation models grew up right. Every model of galaxy formation is, in a sense, a biography written before the full evidence is known. It tries to explain how gas becomes stars, how dark matter shapes structure, how feedback changes growth, and how all of that unfolds across time. Ancient galaxies are where those biographies are being checked against reality. Because they come from such early eras, they reveal whether the opening chapters of our theories are sound. If the predicted timing, brightness, or structure is off, then the problem is not small. It means the foundations of the story may need revision. That is what makes these galaxies so powerful. They are not only objects to admire, they are examiners of our ideas. Each one asks whether we truly understand how the first systems emerged from the young universe. In that sense, the earliest galaxies are almost like stern teachers. They do not care how elegant our theories look on paper. They care whether those theories survive contact with light. Some supposed giant early galaxies turned out to be less massive than feared. When the first reports of some very early bright galaxies appeared, they caused a wave of excitement and unease. If these objects were truly enormous in stellar mass so soon after the Big Bang, then many existing models would face a serious challenge. But brightness can be deceptive. A galaxy can look overpowering without actually containing as much mass as first assumed. Later observations and more careful analysis suggested that some of these early candidates were not impossible giants after all. In some cases, strong emission from gas or intense recent star formation had made them appear more massive than they really were. That is a beautiful reminder of how astronomy works at its best. Surprise comes first, then scrutiny. The result is not disappointment, but refinement. Some galaxies remain strange and important, yet less catastrophic for theory than initial headlines implied. The universe had startled us, then invited us to look again more carefully before we rewrote the whole opening of cosmic history. Better spectra often reveal ancient galaxies are strange, but not impossible. A photograph can make a galaxy look mysterious, but a spectrum tells a deeper story. By spreading light into its component wavelengths, astronomers can estimate distance, identify glowing gases, and infer how stars and matter behave inside a galaxy. This often changes everything. An object that first seemed impossibly massive or unexpectedly mature may look more understandable once its spectrum is measured properly. Emission lines can brighten certain bands. Dust can alter apparent colors. Redshift can place the object more securely in time. What remains is often still remarkable but less apocalyptic for theory than the first image suggested. That is part of the beauty of modern astronomy. The universe is full of surprises, but it also rewards patience. Better spectra do not always remove the wonder. Often they sharpen it. A galaxy can remain deeply unusual while becoming more physically plausible. In that way, spectra act almost like translation tools, turning astonishing distant smudges into specific stories the laws of nature can still recognize. Distance estimates can transform a mystery into a match for theory. In the early days of analyzing a faint remote galaxy, one of the hardest questions is simply how far away it really is. Color can suggest distance, but color alone can mislead. Dust, gas emission, and other effects can mimic the appearance of a more ancient source. That means a galaxy that first looks like a dramatic challenge to cosmology may later turn out to belong to a different era altogether once the distance is pinned down more securely. When that happens, mystery gives way to alignment. The object no longer threatens the timeline in the same way because it fits better into what theory already allows. This is not a letdown. It is one of the disciplined pleasures of science. The goal is not to force the universe to be shocking. The goal is to know what it is. Better distance estimates are often the difference between panic and perspective. They can take a cosmic rebel and reveal it as something extraordinary, but still entirely at home in the universe's wider plan. Ancient galaxies keep teaching astronomers to be bold and cautious together. The earliest galaxies inspire two opposite impulses at once. On one hand, they reward boldness. New instruments, fresh theories, and daring interpretations are needed to push back into such remote epochs. On the other hand, they punish haste. A source can seem revolutionary before later data shows a more ordinary explanation. This tension has become one of the defining lessons of studying cosmic dawn. Astronomers must be imaginative enough to follow the evidence into unfamiliar territory, yet restrained enough not to crown every surprise a crisis. That balance is not weakness. It is maturity. Ancient galaxies demand it because they sit at the edge of what can be observed, where uncertainty is high and the temptation to overstate is always present. In that sense, these galaxies do not just reveal the early universe. They shape the character of the people who study it. They teach researchers to welcome wonder without surrendering rigor, and to move forward with excitement that still knows how to wait. Each new deep field can quietly rewrite the opening chapters of cosmic history. A deep field is, in one sense, a simple thing. A telescope stares at a small patch of sky for a long time and gathers the faintest light it can. Yet the result can be profound. What first looked like emptiness becomes crowded with remote galaxies, each one a message from a different era. In those tiny windows, astronomers can suddenly see populations of ancient systems that were previously unknown or poorly understood. That means each new deep field is not just another picture. It is a fresh sample of the universe's early record. A handful of faint points can reshape how we think the first galaxies formed, how common certain kinds of objects were, and how the young cosmos changed through time. The revisions are often quiet at first, hiding in catalogues and analysis rather than headlines. But taken together, they can alter the opening chapters of cosmic history. One small patch of sky can end up changing the story of everything. The earliest galaxies are forcing astronomy to become more imaginative and precise. Some scientific discoveries reward caution alone. Others reward creativity alone. The earliest galaxies demand both. They push astronomers toward more imaginative models because the old assumptions do not always explain what is being seen. Perhaps black holes began from heavier seeds. Perhaps gas cooled or condensed in unexpected ways. Perhaps early structure assembled through pathways not fully captured before. Yet imagination by itself is not enough. These galaxies also demand greater precision in measurement, calibration, interpretation, and modeling. Distances must be checked. Spectra must be refined. Hidden biases must be exposed. So the field is being stretched in two directions at once. It must become freer in thought and stricter in method. That makes this era of astronomy especially thrilling. The universe is not merely offering new data. It is reshaping the way the science itself has to operate. The earliest galaxies are training astronomy to be more adventurous without becoming careless, and more exact without losing its appetite for wonder. Ancient galaxies were probably surrounded by halos of invisible dark matter. What we see in a galaxy is only part of the story. Stars, glowing gas, and dust make up the visible body. But most theories suggest that ancient galaxies were embedded within much larger halos of dark matter. This invisible substance does not shine or absorb light in ordinary ways, yet its gravity helps hold galaxies together and shape how they grow. In the early universe, these halos were likely among the first major structures to form, gathering unseen mass before ordinary matter settled into them. That means an ancient galaxy may have been only the luminous center of something far larger and mostly hidden. The idea is haunting. Around every visible young system, there may have been a ghostly envelope of matter no eye can see, guiding the motions of gas and stars all the same. To study an ancient galaxy, then, is partly to study a silhouette cast by something invisible. The brightest early lights may have been nested inside vast unseen worlds. Dark matter gave early galaxies the gravity needed to gather gas. Ordinary matter alone has a hard time explaining how quickly the first galaxies seem to have assembled. Gas needs gravity to pull it together, yet the visible matter in the early universe was not enough by itself to build structure at the observed pace. Dark matter helped solve that problem. Long before stars lit up, dark matter halos were already forming under gravity, creating deeper wells that ordinary gas could fall into. Once there, the gas could cool, condense, and begin forming stars. In this picture, dark matter is not a decorative extra. It is the hidden framework that allowed galaxies to become more than scattered clouds. That is one of the strangest truths in cosmology. The visible splendor of early galaxies may have depended on something permanently unseen. Their light, their stars, and their future all rested on invisible gravity, doing its work first. The first galaxies were not built by luminous matter alone. They rose because darkness had already prepared a place for them. Without dark matter, the first galaxies may have formed very differently. It is difficult to overstate how much dark matter shapes the standard story of galaxy formation. Remove it, and the timeline changes. Gas would still respond to gravity, but it would have far less invisible scaffolding to gather around. Structure would grow more slowly, less efficiently, and perhaps in very different forms. The early universe might have stayed smoother for longer, with fewer dense sites where stars could ignite and galaxies could take hold. This thought experiment is useful because it reveals how deeply modern cosmology depends on unseen matter. Ancient galaxies are part of the evidence that something extra was guiding growth from the beginning. Their existence, timing, and distribution all make more sense if hidden mass was present. In a way, every early galaxy is a clue that visible matter did not act alone. Without dark matter, the first galaxies may have been rarer, weaker, or delayed. The luminous cosmos we admire today may owe its early emergence to something we have never directly seen. The earliest galactic scaffolding was likely built from matter we cannot see. Before galaxies became bright, before stars painted space with visible fire, the universe was already building the structures that would later host them. According to the prevailing picture, that first scaffolding was made largely of dark matter. It gathered under gravity into halos and filaments, creating a hidden architecture across the young cosmos. Ordinary gas then flowed into that framework, settling into the deepest regions where stars could eventually form. This means the visible universe may have been built on an invisible design. The phrase sounds poetic, but it is also scientifically profound. The first galactic homes were not improvised out of glowing matter alone. They were shaped by a pre-existing skeleton that could not be seen directly, only inferred through its gravitational influence. That gives ancient galaxies an eerie depth. When we look at one, we are seeing the lit interior of a much larger hidden construction. The first visible structures may have depended on a secret framework already standing in the dark. Ancient galaxies grew where dark matter created the deepest cosmic wells. Not all regions of the early universe were equally favorable for galaxy formation. Some places had stronger concentrations of dark matter, and those concentrations created deeper gravitational wells. Gas falling into such wells could be trapped more effectively, compressed more efficiently, and turned into stars more readily. That means the earliest and most vigorous galaxies likely emerged where invisible mass had already made the strongest foundations. In this view, dark matter determined the landscape of opportunity. It shaped where growth would be easiest and where cosmic structure would blossom first. The visible galaxy was then the bright announcement that one of those hidden wells had succeeded in gathering ordinary matter. This helps explain why ancient galaxies were not scattered at random. Their locations reflected an underlying pattern of unseen gravity. Some corners of the young universe were better prepared than others. The first luminous systems rose where the invisible terrain was deepest, and their light-marked places where hidden structure had already done its quiet work. Gas fell into those wells, then stars lit the darkness from within. There is something almost theatrical about the sequence. First, the invisible wells formed, shaped by dark matter gathering under gravity. Then, ordinary gas began to descend into them, drawn inward from the surrounding cosmos. As the gas collected, it cooled, thickened, and eventually collapsed into stars. Only then did light appear. So the first galaxies may be understood as a kind of ignition inside hidden gravitational basins. The darkness came first, not as emptiness, but as structure without light. Then matter flowed in and turned those unseen shapes into visible cosmic landmarks. That progression makes the first galaxies feel even more dramatic. Their starlight was not random decoration. It was the visible outcome of an earlier invisible preparation. A galaxy announced that a dark well had become a luminous home. The idea is deeply beautiful. Light emerged not in open emptiness, but from within gravitational hollows that had quietly been waiting. The earliest galaxies were darkness made visible from the inside out. The cosmic web fed ancient galaxies through long hidden rivers of gas. The universe is not arranged like isolated islands floating in featureless emptiness. On the largest scales, matter forms a vast network of filaments and nodes, often called the cosmic web. Along those filaments, gas could stream toward growing galaxies, providing fresh fuel for stars and further development. In that sense, ancient galaxies were not only collecting what happened to be nearby, they may have been fed by long, narrow supply lines stretching across intergalactic space. These hidden rivers of gas are one of the most compelling features of modern cosmology. They turn galaxy growth into something more connected and dynamic. A young galaxy was not a sealed object living off a fixed inheritance. It was part of a larger flow system, drawing sustenance from the web around it. That makes the early universe feel less like scattered points of light and more like a living structure with circulation. Some of the first galaxies may have thrived because the cosmos itself kept sending material their way. Some early galaxies sat at the crossroads of that enormous web. In any network, some intersections matter more than others. The same may be true for the cosmic web. Where several dark matter filaments met, gravity could gather more gas and more small structures into one region, creating especially favorable conditions for galaxy growth. Early galaxies in those locations may have had access to richer inflows, more interactions, and greater opportunities to become large or complex quickly. That gives them a kind of cosmic geography. Not every galaxy was born on equal ground. Some sat in quieter stretches of the web. Others occupied crossroads, where material and influence converged. Those crossroads may have been the seeds of later galaxy groups, clusters, and large-scale structures we see today. The idea is wonderfully grand. A distant ancient galaxy may owe its history partly to where it stood in a vast invisible network spanning millions of light years. Its brightness, growth, and future could all be shaped by its place in a cosmic map far larger than itself. Ancient galaxies were not isolated sparks, but knots in a larger structure. It is easy to think of a distant galaxy as a lone beacon in empty space. The deeper truth is more interesting. ancient galaxies were embedded in a larger cosmic pattern. They were knots where matter had concentrated within the web of dark matter and gas stretching across the universe. That means their existence was tied to a broader architecture. A young galaxy did not merely appear on its own. It occupied a position in a much larger network of filaments, neighboring halos, and future structures still taking shape. This changes the emotional texture of the early universe. Instead of isolated sparks scattered randomly through darkness, we begin to see a connected system whose brightest nodes marked deeper hidden relationships. Each galaxy was local, yet also structural. It belonged to a wider design. That design governed how matter flowed, where future growth would happen, and which regions would become especially crowded or massive. In the early universe, every visible knot of light hinted at invisible connections extending far beyond it. The largest galaxies may have grown where the cosmic web was thickest. Not all parts of the cosmic web carried the same weight. Some filaments were denser, some intersections richer, and some regions more effective at channeling gas and small structures into one place. In those thicker portions of the web, galaxies may have had access to more fuel, more mergers, and stronger gravitational support for rapid growth. That could help explain why some systems became unusually large or active early on. Their success may not have come only from internal efficiency. It may also have come from privileged placement in the universe's hidden infrastructure. This is one of the great lessons of large-scale cosmology. Location matters. A galaxy's destiny is shaped not just by what happens inside it, but by the flow of matter around it, across enormous distances. The largest ancient galaxies may therefore be read as markers of the web's richest regions. Their brightness and mass tell us where the invisible cosmic landscape was thickest and where the universe most strongly favored growth. Tiny dwarf galaxies may preserve clues to the universe's first systems. The biggest galaxies draw the eye, but the smallest may carry some of the oldest memories. Tiny dwarf galaxies are simple compared with giants like the Milky Way. Many contain relatively few stars, weak structure, and limited chemical enrichment. That simplicity makes them precious. In some cases, they may preserve features closer to the earliest galactic conditions than larger, more heavily altered systems do. A giant galaxy is like a city rebuilt again and again over thousands of years. A dwarf can be more like a small settlement left half unchanged. Its stars may retain chemical signatures from early generations. Its structure may reveal what modest galaxies looked like before repeated mergers and long internal evolution transformed them. That is why astronomers value these faint systems so highly. They may not dominate the sky, but they can preserve a more direct connection to cosmic beginnings, holding clues that larger and more glamorous galaxies have long since erased from their own complicated histories. Some nearby dwarf galaxies act like living fossils of ancient times. Not every relic of the early universe lies impossibly far away. Some may be orbiting close by in our own cosmic neighborhood. Certain nearby dwarf galaxies seem to have changed comparatively little over billions of years, which makes them feel almost like living fossils. They still contain very old stars, low amounts of heavy elements, and simple structures that hint at an ancient style of galactic life. Of course, they are not frozen in time. Nothing in the universe truly is. But they may have avoided the repeated major disruptions that reshape larger galaxies. That relative quiet makes them valuable. By studying their stars, motions, and chemistry, astronomers can glimpse conditions that may echo much earlier eras. It is a wonderful twist of perspective. To learn about the first galactic chapters, we do not always need to look only to the edge of the observable universe. Sometimes ancient habits survive nearby, hidden inside small, faint companions that still carry the mood of a much older cosmos. The Milky Way may have swallowed many ancient galaxies long ago. Our galaxy did not grow as a single, peaceful object. It likely became what it is by consuming many smaller systems over immense spans of time. Some of those victims were ancient galaxies that once moved through space as independent worlds with their own stars, gas, and dark matter halos. As they fell too close, the Milky Way's gravity stretched them, stripped them, and eventually folded much of their matter into the larger galactic body. Their identity was lost, but their substance survived. This gives our galaxy a layered and almost haunted quality. It is not just one thing. It is partly an archive of earlier galaxies that no longer exist in separate form. Some of the stars in the halo, thick disk, or outer reaches of the Milky Way may once have belonged elsewhere. So when we look at our galaxy, we are also looking at the aftermath of long galactic cannibalism, where ancient systems were not erased completely, but absorbed into a grander and more complicated whole. Streams of stars around our galaxy are rubble from lost galaxies. The sky around the Milky Way is not as tidy as it first appears. In its halo, astronomers have found long streams of stars stretched across space like ghostly trails. These are not random decorations. Many are the shredded remains of smaller galaxies that wandered too near and were pulled apart by gravity. As those systems dissolved, their stars were drawn out into elongated streams that still remember the path of destruction. There is something deeply moving about that image. A galaxy can die, yet leave behind a visible trace of its final unmaking. These stellar streams are like ruins scattered not on land, but across the sky. They tell us that the Milky Way has a violent appetite and a long memory. By mapping their motion and chemistry, astronomers can reconstruct lost galaxies that no longer exist as separate bodies. Even in death, they continue to speak, their stars laid out like evidence across the dark, preserving a story of capture and collapse. Studying nearby relics can reveal what the earliest galaxies were like. Looking farther away lets us see earlier in time, but looking nearby has its own special power. Some local relic galaxies and ancient stellar populations can be studied in far greater detail than the most distant objects ever could. Astronomers can measure the chemistry of individual stars, trace their motions, and reconstruct pieces of their formation history with remarkable precision. That detail acts like a bridge. If a nearby system has preserved primitive traits, it can help us interpret what the earliest galaxies may have been like when the universe was young. This is one of the most elegant strategies in astronomy. It combines deep time with close inspection. Remote galaxies show us direct, ancient light. Nearby relics let us read the fine print. Together they make a stronger story than either could alone. By examining surviving local traces of old galactic conditions, astronomers can infer how the first systems behaved, what kinds of stars they formed, and how simple beginnings later blossomed into the richer universe we know. Not every ancient galaxy vanished. Some survive as faint companions today. It is easy to imagine that the earliest galaxies were all swallowed, shattered, or transformed beyond recognition. Many were. Yet some may still survive, quietly orbiting larger galaxies as faint companions. These survivors are usually small, dim, and easy to overlook beside the splendor of giant spirals and ellipticals. But their modest appearance can be deceptive. A faint companion may contain stars that formed in very early epochs and preserve chemical conditions from long ago. That makes it a kind of endurance story. Not every ancient galaxy became part of something larger or disappeared into streams of debris. Some held together, however tenuously, and made it all the way into the present day. Their continued existence is astonishing when you consider how turbulent galactic history can be. They have endured tidal forces, changing environments, and billions of years of cosmic motion. Today they drift in the shadows of giants, not glamorous, not bright, but still carrying pieces of the universe's earliest memory inside them. Small galaxies were not failures, they were the building blocks of giants. In human thinking, small often sounds lesser, as though it represents an incomplete version of something greater. Galactic history tells a different story. Small galaxies were not failed attempts at grandeur. They were essential parts of how grandeur emerged at all. Through mergers, accretion, and gradual assembly, larger galaxies were often built from the material, stars, and dark matter of many smaller predecessors. That means the universe did not begin by making only giants. It began by making numerous modest systems that later contributed to the rise of massive ones. Their role was foundational, not secondary. This changes how we should picture cosmic history. A giant galaxy is not simply a bigger thing. It is often a composite, made from many earlier, smaller chapters joined together over time. So the small galaxies of the young universe deserve respect not because they sometimes survived, but because even when they did not, they shaped what came next. They were the bricks, not the mistakes, of galactic architecture. Ancient galaxies may have come in swarms, not just splendid standouts. When we talk about the early universe, it is tempting to focus on the spectacular few, the bright galaxies, the strange quasars, the objects dramatic enough to grab attention. But cosmic history was probably not built by rare standouts alone. Ancient galaxies may have existed in swarms, with numerous small systems gathering, clustering, and interacting across young cosmic environments. Some were brighter than others, but many may have been faint, crowded together, and deeply involved in the larger work of structure formation. That possibility changes the mood of the early universe. Instead of a mostly empty darkness punctuated by a few exceptional lights, we begin to see a busier scene, full of modest galaxies arriving in groups, affecting one another, and helping build future clusters and giant systems. This matters because numbers can matter more than spectacle. A swarm of small galaxies can reshape the universe even when no single member seems extraordinary on its own. Ancient cosmic history may have been less lonely and far more communal than we once imagined. The universe likely made many more tiny galaxies than bright, famous ones. The galaxies most likely to make headlines are the luminous and unusual ones because they are easiest to detect and hardest to ignore. But astronomy strongly suggests that the universe probably produced far more tiny galaxies than spectacular bright ones. That pattern fits what we see in many parts of cosmic structure. Small objects are numerous. Giant showpieces are rarer. In the early universe, countless diminutive galaxies may have flickered into existence, formed modest numbers of stars, and then either survived quietly, merged, or faded from easy view. Their sheer abundance may have made them more important than their individual faintness suggests. This is one of the humbling truths of cosmology. The universe is not mainly a parade of famous extremes. Much of its history may have been carried by countless little systems working below the threshold of popular attention. The bright galaxies help us notice the era. The tiny ones may have been the era's real majority, quietly shaping the opening structure of everything that followed. Some of the oldest galactic survivors are now the easiest ones to overlook. Age does not always announce itself with grandeur. Some of the oldest galactic survivors may now be faint, sparse, and visually unimpressive beside bright, modern giants. That makes them easy to miss both in the sky and in the imagination. Yet those overlooked systems can be among the most historically valuable objects in the local universe. Their stars may preserve ancient chemical patterns. Their weak structure may reflect an origin in far earlier cosmic conditions. Their very faintness can be a clue that they have lived long, quiet, and relatively undisturbed lives. There is something almost poetic in that. The ancient witnesses are not always the loudest or most majestic. Sometimes they are the small, dim companions hanging at the edges of more glamorous galaxies. To notice them requires patience and humility. They remind us that cosmic importance and visual splendor do not always travel together. Some of the universe's deepest memories now reside in systems so modest that a casual glance could pass right over them. Ancient galaxies can reveal time, chemistry, gravity, and the history of light. Few objects in astronomy carry as many layers of meaning as ancient galaxies do. They are time capsules because their light comes from the distant past. They are chemical records because their stars and gas preserve evidence of what elements existed and how quickly enrichment occurred. They are laboratories of gravity because their growth, shape, and motion reflect the pull of visible and invisible matter alike. And they are also records of light itself, because the radiation we receive has been stretched, filtered, and transformed by the expanding universe. That combination makes them extraordinary. A single remote galaxy can tell us how old the universe was at the time, how matter was assembling, what stellar processes had already taken place, and how space changed the message during its long journey. They are not just distant objects. They are stacked testimonies, each carrying several stories at once. To study them is to read time, matter, force, and light in one remarkable source. Every deep image of them is really a map of time. A deep astronomical image does not work like an ordinary photograph. On Earth, a photograph captures different objects as they exist at almost the same moment. In a deep view of ancient galaxies, each point of light arrives from a different era. One galaxy may be from a time when the universe was already mature. Another may come from a period far earlier, when cosmic structure was still new. That means the image is layered in time, as well as in space. Looking across it is a little like looking down through stacked ages of cosmic history all at once. The nearest bright foreground objects and the faintest remote smudges are not neighbors in any ordinary sense. They are separated by immense differences in epoch. This gives deep fields their almost dreamlike power. They are not merely beautiful pictures. They are mosaics of history, where each dim source marks a different chapter. In that sense, every deep image is not just a scene. It is a time map written in light. The farther a galaxy lies, the younger the universe around it appears. Distance in astronomy has a strange consequence. Because light takes time to travel, a very remote galaxy is seen not in its present condition, but in the state it had when the universe itself was younger. The farther away the source, the further back the view reaches into cosmic history. So a galaxy at immense distance is not simply located in a remote place. It is embedded in an earlier version of the universe. That means the environment around it was different too. The average chemical richness was lower. Structure was less mature. The great later generations of galaxies and stars had not yet had time to reshape everything. This is one of the most beautiful features of cosmology. Space becomes a pathway into age. A distant galaxy does not just tell us about itself. It tells us about the world it inhabited, a universe younger than our own current moment. The farther we look, the more the surrounding cosmos itself seems to become newly born. Ancient galaxies let us watch structure emerge from near-primitive cosmic conditions. Modern galaxies exist in a universe already shaped by billions of years of stellar birth, chemical enrichment, mergers, and large-scale evolution. Ancient galaxies take us back to a far simpler stage. The universe then had fewer heavy elements. less finished structure, and a much shorter history behind it. That is why these galaxies are so revealing. They let us see what happens when gravity begins building complex systems out of comparatively primitive starting conditions. We can watch gas become stars, small objects join into larger ones, and rough forms begin the long path toward later galactic diversity. It is like seeing architecture emerge before the city is finished, while scaffolding, foundations, and first walls are still visible. The simplicity of the starting point makes the process easier to understand and more dramatic to witness. Ancient galaxies show the universe at a formative moment, when the leap from raw matter to organized structure was still underway and complexity had not yet become ordinary. They're like records both where they were and when they were. A galaxy's light is more than illumination. It is information encoded in motion, distance, and age. By the time ancient galactic light reaches us, it carries clues to where the galaxy was in the universe and when in cosmic history that light was emitted. Redshift reveals how much the universe has expanded during the journey. Brightness and spectrum help estimate distance, composition, and activity. Together, these details turn light into a historical document. It tells us not only that a galaxy existed, but where it stood in the evolving cosmic landscape and in which chapter of universal time it was shining. That dual role is part of what makes ancient galaxies so mesmerizing. Their light is not simply a picture. It is a message with coordinates in both space and history. We are not merely observing an object. We are receiving evidence about a place and an era simultaneously. In that sense, every ancient galaxy sends a beautifully precise note from a lost moment. We do not see ancient galaxies as they are, but as they were. This is one of the defining wonders of astronomy. In daily life, seeing feels immediate. You look at something and trust that you are meeting it in the present. With ancient galaxies, that intuition fails. The light we detect left them billions of years ago, when the universe itself was younger and the galaxies were in earlier stages of their lives. Some may have changed beyond recognition since then. Some may have merged, grown, or disappeared into larger systems. Yet the light arriving now still preserves their older condition. So astronomy becomes an encounter with vanished presence. We are not catching up with these galaxies in real time. We are witnessing preserved moments from lives that continued long after the signal began its journey. That creates a strange mixture of intimacy and distance. We can study them in detail, yet only in their past form. Ancient galaxies remind us that seeing across vast space is really a form of remembering, carried out not by minds, but by light itself. The first galaxies turned a simple universe into a richer one. At the start, the universe was far simpler in composition and structure than it is now. There were only the lightest elements in abundance, and there were no long histories of stars, planets, or chemistry behind anything. The first galaxies changed that. They gathered matter into durable systems, formed stars in large numbers, and began cycling material through stellar lives and deaths. In doing so, they made the universe more varied. They added complexity to its chemistry, structure to its matter, and history to its visible contents. This was not a small upgrade. It was a profound transformation. A simpler cosmos gave way to one capable of making increasingly diverse objects, from later galaxies to rocky worlds to living organisms. That is why the first galaxies matter so much. They were not just among the earliest visible things. They were engines of enrichment, organization, and possibility. They changed the universe from a relatively plain beginning into something layered, fertile, and much more interesting. Ancient galaxies began the long chain that eventually led to planets and people. No person looking at a remote early galaxy can avoid the deeper implication. Those systems helped begin a sequence of events that would, after immense spans of time, lead to planets, oceans, chemistry, biology, and human minds capable of looking back. The path was long and indirect, but it starts there. Ancient galaxies formed stars that created the heavy elements needed for rocky worlds. Later generations of stars inherited that material. Planetary systems formed. On at least one small world, life arose and evolved into beings who could ask where they came from. This is not mystical. It is physical ancestry on the largest scale. The atoms needed for planets and bodies had to be made somewhere, and the early galaxies were among the first great places where that became possible. That makes them more than scientific curiosities. They are part of our deep origin story. When we study them, we are tracing the opening links in a chain that eventually became us. To study ancient galaxies is to watch the universe learn complexity. The young universe began with relatively simple ingredients and broad physical rules, but complexity did not appear all at once. It had to emerge. Ancient galaxies let us witness that emergence in action. Inside them, gravity gathered matter into structure. Stars turned simple elements into richer chemistry. Repeated cycles of formation and destruction produced increasingly intricate environments. Over time, the universe moved from raw starting conditions toward layered systems capable of supporting later worlds, and eventually life. That is why ancient galaxies feel so intellectually satisfying. They show not just objects, but a process of learning, if we borrow that word in a poetic sense. The cosmos was discovering what it could build. First came primitive structure, then more elaborate histories, then more varied matter, and later the possibility of astonishing things like planets and biology. To look at an ancient galaxy is to catch the universe in an early lesson, still working out how to become more than a simple beginning. The oldest galaxies are our clearest clues to how everything began. We cannot watch the Big Bang itself unfold in any direct, ordinary sense, and we cannot visit the first moments of cosmic time. But the oldest galaxies bring us as close as nature seems willing to allow. They formed in the aftermath of the earliest conditions, while the universe was still young enough to retain the imprint of its beginning in visible structure. Their light, chemistry, brightness, and environments all carry clues about how matter first gathered and how the first luminous systems emerged. That is why they are so precious. They do not tell us everything, but they tell us more than almost anything else can. They stand near the beginning of the observable story, offering evidence from a time when the rules of later cosmic history were only just taking hold. To study them is to approach the threshold of origins. They are not merely old objects. They are some of our best surviving witnesses to how the universe first began turning into the world we know. As we drift away from these distant galaxies, it helps to pause and take in just how far we've traveled together. We began at the edge of time itself, where the first galaxies flickered into existence, gathering light out of a young and restless universe. We watched them grow from simple beginnings, shaping stars, forging the elements, and slowly transforming darkness into something richer and more complex. We followed their light across billions of years, through expansion, through change, until it finally reached us here, tonight. And somewhere along that vast journey, those early galaxies set everything else in motion. The chemistry of planets, the structure of galaxies, even the quiet presence of the world around you now. So as you rest, imagine those ancient systems still out there, their light continuing its long, silent voyage. Some of it still traveling, still crossing the deep, waiting to arrive somewhere, sometime, just as it arrived for us. If you enjoyed this journey, you might like to explore another video waiting for you on the screen. And if these quiet explorations bring you a sense of calm or wonder, you're always welcome to like, subscribe, or share a thought below. It helps guide others here too, one sleepy soul at a time. But for now, there is nothing more you need to do. Let your thoughts slow. Let the vastness fade into the background. And let yourself settle into rest as the universe continues on without asking anything more from you. Sleep well and good night.